He comes from Torino, Italy. He did his PhD 2 years ago, 1 year ago, 1.5 years ago, under the supervision of Guido Feta. His main research interest is, in general, the statistical properties of turbulence, and in particular, turbulence in the ocean. Today he will be talking about some properties of floaters in the oceanic setting.
Okay, thank you. Welcome everybody. So it's a pleasure to be here. And today I will talk about some research interest, research work that I developed during my PhD, basically. So you will know at the end what I meant to say when I talk about floaters and isopycnal surface. I hope. And so, starting from the beginning, we would like to model somehow in a simple way the ocean dynamics. And to do that from a fluid dynamical point of view, you start with the Navier-Stokes equation. But it maybe it's too simple. So if one wants to add some other ingredients in order to be somehow more realistic, but not too much, one can first think about to consider density variation. In the ocean, density variation are mainly given by temperature and salinity differences. And this can be evident by looking at the vertical profile of the density within the water column. And you may observe that just below a mixed layer where density is almost homogenized by turbulence, which is pretty high near the surface, there is a layer which we are interested in, where density is strongly influenced by gradients. So it depends really strongly on the depth. Basically, here you have light water standing on top of denser and denser water, which means that the fluid is in a stable configuration. And you can try to somehow to treat this behavior in density in the simplest way using a linear behavior with the depth. So you have the density is not longer a constant, but it depends on the depth with a mean gradient gamma, and then you also add a fluctuation on this mean gradient in order to observe really small scale variation due to turbulence. And so this is what is called the Boussinesq equation. And some main features of this new system, differently from simply Navier-Stokes equation, is that isotropy is no longer somehow conserved, and this is because of gravity. So gravity breaks down isotropy. And this can be evident by looking also at some simulation down here. You may start to form really layer structures, so much more elongated in the horizontal direction rather than in the vertical. And also another important aspect is that beside turbulence there is also the presence of waves. So there is a coexistence between a turbulent state and waves. So it's already a complex system, even though we try to modelize it really simple. And yeah, so talking about a little bit of simulation, it's really a complicated slide, but I will make it simple. What in principle is important to remind when we talk about simulation of turbulence in general is that you have to think about the separation between scale. So when you think about turbulence, we always think about injection of energy at a given scale, usually large scale, then some transfer at intermediate scale, and then the dissipation at small scale. And the Reynolds number, which basically measures the intensity of turbulence, is basically tell you what is the separation between these two scales. Much more they are separated, much more you have turbulent flows, basically. And this is somehow the state of the art for stratified turbulence. where this dot indicate somehow the real parameters for the ocean. And these the small dots are the simulation, so we are somehow pretty far from reality, which is not wrong in principle. I mean, all these simulations are basically can resolve only a part of the ocean. Let's say 1 meter per cube of the ocean, so a small part, not the entire system, of course. And well, so more recently, an application of this simulation for turbulent flows can be found in, for instance, ocean biophysics. Well, basically, inside 1 meter cube of water inside the ocean, there is still enough process going on. From the biological point of view, so there are some many microorganisms living there, and where phytoplankton are the most important for our studies. They are located between a range of 1 micrometers to hundreds of micrometers. And as you can see, they live basically in a very viscous world. Someone say that swimming for this individual is basically for a human to swim in a pool of honey. So it's really viscous. From the energetic point of view, it costs really much. But nevertheless, at higher scale, turbulence affect the life of this microorganism by looking also these images by mixing and create heterogeneous distribution. And this is important so this is an implication for all the life of phytoplankton, for encounters between individuals of the same species for reproduction, encounter with nutrients, escaping from predators, and so on. So somehow this is the motivation between turbulence and biophysics. And so I said that we are most interested in phytoplankton. Inside phytoplankton there is a major class which is diatoms. Somehow in this slide I would like to motivate the idea to study the effect of stratification and density variation within with a small class of individuals that maybe find crucial strategies for that. And in this class, so we would like to select particles that are not swimming, so non-motile particles. And this type of family of species elaborate usually different strategies to move in the fluid, and basically they change density. So somehow this is the relevant point. And they found also to be somehow correlated with the pycnocline, so this region where the density is strongly varying through the depth. Again, continuing with this biological motivation, sometimes these species are able to aggregate in very dense layer where the concentration is pretty high. They are vertically extend by few centimeters to few meters, but they are really long extent in the horizontal plane, up to kilometers. And as you can see from the pictures above, you may observe that the peaks, the concentration which is measured in terms of chlorophyll concentration, because they are plants, so they do photosynthesis. You can see that the peaks, the concentration in the peaks is almost 10 times the background, so it's really concentrated. And in these other studies, they found that the peak, so the highest concentration is found to be correlated somehow with this stronger change in the density. And these other two always ship field experiments. They observe the motion of an internal waves, so basically something a physical process in the ocean, but was made visible by the fact that on these waves, suspended particle was basically surfing this way, so they make visible by using a standard a sonar technique. So it's basically an acoustic backscattering. They are able to reveal all the particles that are suspended near the ship. So there is somehow a really strong interplay between biology and the physical process in the ocean.
Sorry, you missed the definition of pycnal line.
Yes, pycnal line is this region where the word pycno means density in Greek, and yeah, so is the region where is characterized by a strong gradient in density, basically. And yes, I was talking about phytoplankton layer. So the mechanism that may lead to this film formation are not unique, and of course we are primarily interested in the one based by buoyancy, but it's not the only one. Some other mechanisms are mainly due to biological cause, and some other are somehow a combination between physical and biological mechanism. For instance, for the buoyancy, one may found that the distribution that one should obtain for this layer must be a Gaussian. And it's somehow interesting because depending on the species, so for instance, the buoyancy is a candidate mechanism for non-motile particle, for particles that are not able to move. So basically they are only just allowed to fall down in the water column and accumulate at a given layer, at a given level, sorry. So depending on the species, there are some mechanisms allowed, and given a mechanism, one can do some calculation in order to find a particular form for the distribution. And of course, this reasoning can be applied also backward. So imagine you have an experiment and you compute the distribution, but you don't know the mechanism and the species. Maybe. And somehow you can infer some of the property with this reasoning. So coming to the work, what we want to do is to do a simulation with a stratified fluid, and for this we integrate this Boussinesq equation, where we have here the evolution for the velocity of the fluid, and coupled with the evolution for the density, for the fluctuation of the density field. And this is a snapshot, a vertical profile of the typical field of density that one may found. And the important thing is that there is one dimensional parameter which controls the level of stratification, the strength of this stratification, and of course Reynolds number, which controls the turbulence. And for the particles, we want to seed our system with particles. We have to use the so-called Maxey-Riley equation, which describes the motion of particle. So the velocity of the particle v is equal to a couple of terms is given, of course, by the fluid acceleration plus the added mass. So the fact that depending if the particle is light or heavy than water, there is a different amount of water that moves around itself. Then there is the Stokes drag, again depending on its inertia, and the buoyancy, which is correlated to gravity. And yeah, so here we have two parameters to say everything. The Stokes times controls the inertia of the particle. So it is the time needed for the particle to adapt itself to the fluid velocity. And beta is the density contrast, which is already dimensionless parameters, and controls basically the difference between the fluid density and the particle density. And so depending on the particle density, we have this value. We are mostly interested in neutral particles, so where particles are almost the same, has almost the same density of the surrounding fluid. But density is not homogeneous, it's not constant this time. And somehow so we have to treat this equation in the same way we have treated the fluid equation. So we have to be consistent and apply the same approximation. And the approximation that we made so far from the density field is called the buoyancy approximation. I will go too much further on it, but basically what we do is to consider the gravity acceleration much larger than any other acceleration in the fluid. And in particular, it works like this. Density fluctuations are usually small, but they become important when they are multiplied by gravity. And so beta, which we have chosen to be 1 mostly, is corrected with this term, which gives you a correction with the density variation. So it's 1 when multiply this term, but it's not 1 when multiply g. And so we have somehow a correction given by a correction for the particle motion depending on the density variation. We do one more assumption by assuming that the particles are small. And this is somehow relevant for phytoplankton. And if particles are small, basically means that they are not inertial. So they basically follows the fluid without any resistance. And so this Stokes time is made small. And what we do is to end with a much simpler system, which is basically a first order differential equation. And if you study this dynamical system, you can observe that the fluid follows almost the velocity fluid, so it's almost a tracer, plus this term, which represents a relaxation, an exponential relaxation towards an object, which is a surface. And this is the definition of isopycnal surface. So it's a surface with constant density. If you remember, so the mechanism for buoyancy, the particles are supposed to fall down until they reach a level where they are with the same density with the surrounding fluid. In this case, this level is not constant, but it's moving. And so this gives you somehow a fixed point, which is a dynamical fixed point, so it's continue to moving. And if you compute the divergence of this dynamical system, this tells you the contraction of the phase space, so if the system is conservative or not, and you find out that the system is dissipative indeed. And the contraction is correlated with the density variation, in particular with the gradients, vertical gradients. But let's do some. Let's see. So this is a visualization of a simulation. This is the initial condition where particles are distributed homogeneously in space. And in the first moments, you will see the particle fall to reach or rise to reach the middle plane, where is supposed to be the equilibrium level, but this level is moving. And moreover, on it, you see that particles start to cluster, so the distribution is not trivial. Is yeah, it's linear.
You put a linear density.
Yes. And somehow is we only integrate the fluctuation, so it's somehow invisible. Let's say okay. So it's some other visualization of a given time where particle somehow here the system is already stationary, so they do not fall anymore, particles, but they reach this layer and in a statistical sense is stationary. So you can study this distribution. Yeah, first of all, we can observe some vertical cut of in order to explore the parameters. We have two parameters. The first one, Froude, controls the stratification. So it's a physical parameter, only based by fluid properties. And the other is this R, which indicates a relaxation number. So is the relaxation of the particle to adapt to this surface. As you can see, so moving in the vertical direction, we are changing stratification.
Vertical cut?
Vertical cut, yeah. And just to be clear. So moving in the vertical in this axis, we are changing stratification. So you can see that the morphology of the surface, which is indicated in black dots, is changing. And with a weak stratification, you have this really complex contour for the surface. Somehow it's not even a surface because there are also bubbles separate from the surface. And you can see that, for example, in this first column, relaxation time is pretty small, and you can see that the particles are really stick to the surface. Otherwise, moving in this direction, you may observe that particles start to be more dispersed above and below the surface. So imagine you can average on the horizontal axis and then compute the distribution of the vertical position. And the vertical position is fine to be distributed with a Gaussian, as other previous study were somehow confirm that using this mechanism based on buoyancy should be somehow give a Gaussian distribution. And the standard deviation is found to be proportional with the stratification. And you can observe that the other parameter, the R, capital R, is not counting too much. So there is only a small correction. The main dependence is given by stratification. So this means that somehow the type of species, so the type of relaxation time needed to reach the layer is not really important. Once they reach the layer, they basically are all the same. So, okay. And we can try to understand this linear behavior with the Froude numbers, with the stratification. And here somehow the theory behind stratified turbulence help us. Because there is a typical scale for which potential energy, so the displacement of fluid particles compensate the potential energy and the kinetic energy. So this is the typical displacement where a fluid, isopycnal surface is distorted somehow, and is found indeed to be linear again. So this is the distribution now for this family of curves of surface, and is found to follow the same behavior. In particular, when particles are really stick to the surface, they follows all the property of the particles are given by the surface properties. Otherwise, if there is some delay, some more a slower relaxation time, there is a discrepancy between the two statistics. And here is another type of quantity that one may observe. Is again a distance, but now it's a relative distance between particle position and the surface. So it's a relative distance, and now you may observe that they are not all Gaussian. There are some large tail, and if one indeed try to calculate the equation for the evolution of this quantity, found out that in principle, depending on the sign of this term, then can be also an inversion. So also an escape, not only a relaxation. And so this tail, they are given by events where particles are ejected from one branch of the curve, and suddenly they appear to fill a different distance, and so they record a event in the tail. And this is somehow the same as Willy Coyote's experience for a really small time. So in the order of relaxation time, particles may experience a large distance than usual, and then they start to fall again. So these are all quantity at large scale, but now we can also compute some small scale quantities in order to characterize the clustering, the fractal clustering, because as I said before, the system is dissipative. So in principle, it relaxes on a subset, which is usually is a fractal, as you can see already from the picture. And to do that, we compute the so-called correlation dimension, which is basically the probability to find the two particles at a distance less than a given distance. And in the small scale, it should scale like a power law. This is only true so for small scale, basically, where the fluid is smooth. And we can collect this, basically this exponent, and plot it as a function of the parameters. And one found out that now these quantities, this correlation dimension, which characterize the fractal clustering, now depends mostly on the other parameters, so on the Lagrangian, let's say, parameter, the relaxation time, and do not depend too much on the stratification. So because the small scale are not really affected by stratification. with a small explanation. And you have that in the limit of large R, you recover the limit for tracer particle. And tracer usually are distributed in all the space, so they fill the three-dimensional space, and so they have to go in the asymptotic limit towards dimension 3. Otherwise, in the other direction, you reach really a strong clustering in some cases. We do also, well, this is somehow trying to link this study with something more real. So trying to somehow consider the typical parameter that we have used in the simulation, and compare it with the experiments. It's very different. It's very different and very difficult. And we find out in this article all these parameters, and we suggest that should be a clustering for this kind of events, but it's really difficult. Otherwise, we continue to do simulation, and we extend the model not only in the limit for small Stokes number. Now we integrate the entire equation, the complete model somehow. And here's the most, I think, the most important result. Here you can see that comparison between the two models. So in black dots you have the previous model, so the first order equation, ordinary equation. And now the complete model is able to catch not only one branch of this curve, but also the other branch for inertial particles now. And as you can see, there is a minimum which somehow reminds of, for those of you that knows about inertial particles, the fractal dimension has a similar behavior, but there are differences. In particular for the limit now, again, for small Stokes. Usually, the fractal dimension is known to scale as a Stokes square, but in this case, with the action of gravity and buoyancy, we observe a different scaling, and which is proportional simply to is simply linear with Stokes. And also the collapse is in some cases pretty good, which confirm. So this branch of the curve is the same as I showed before. Yes, it's the same of this one, but it's plotted in a different way. Okay, so we try to understand this linear behavior by using a really simple explanation, using a Lyapunov dimension, which is, of course, is not the correlation dimension, but can be really similar. And for those of you that not remember what this is, basically the Lyapunov exponent measure the dimension of the attractor. So is the point that you can find with an interpolation between the dimension corresponding to the sum of the exponent that still gives you a positive sum, so meaning that the space for this d-dimensional volume is still growing, and the space at d+1 volume that do not expand anymore. So in the middle, there should be the correct dimension of the attractor that do not expand and do not contract. So it's the real dimension of the attractor. And by doing some very simple calculation. And the important thing is that that simplify a lot the things, is that for continuous system, so we have three Lyapunov exponents. The first one is the largest, so it gives you the chaotic behavior, so it must be larger than 0. But there should be at least one equal to 0, and the others should be negative in order to have a dissipative system, I think. And if you do this, you can basically find that yeah, the Lyapunov exponent scale with 1 over r, so is a no, not linear, but yeah, 1 over r is the opposite parameter, but yeah. So we do also a more complex study on the thickness of this layer, also for inertial particles, but I think it's not important here. I got to conclusion. The conclusion are that so we characterize this layer. We identify that some of large scale are ruled by stratification, while at small scale fractal clustering is mainly controlled by Lagrangian parameter, so by relaxation time of the particles. Here there are two publications, and I would like also to give you some perspective, just ideas that I have in mind. Some ideas also come from previous conference, and people tell me that maybe it's interesting to do things. For instance, to study a system with only waves, maybe random waves, and to see what are the differences between this case with turbulence and not. And this is also interesting for engineer application, that there are many environmental engineers that are interested in somehow understand the transport of particles in pelagic ecosystem and like that. And a more physical study on, for instance, on statistical geometry of this isopycnal, I think is still debating. And a possible extension of this Lagrangian model should be to include an active control by particles to change their buoyancy, so to change their density particles. That's all. Thank you.
Questions?
When you characterize the fractal characteristics of the simulation, I've never seen, I mean, this is a very anisotropic object. I've never seen a description of,
Yes, yeah.
this. So the fractal dimension 3 can be because particles are in 3 dimensions, or because particles are on a surface and the surface is folded in 3 dimensions. They are very different.
No, well, it's
is there any study distinguishing between the scaling of the
well, as you can,
the density on the surface and across the surface? Is there any way to distinguish that?
a density.
Particles maybe on a surface,
Yes.
and the surface can be very strange, and this influences the fractal dimension. Or particles can be out of the surface.
Yes,
It's a different mechanism, but can give the same dimension. So I don't know.
Yes, it's true. Yeah, it's true.
There is any way or any study to distinguish the two types of clustering?
Maybe there must be somehow one has to compute the correlation between particle position and position of the surface in order to understand if it's random. If it's random some layer around the surface, you will have that particles are not correlated with the surface. Otherwise, if it's the surface that is really rough and particles on it are stick to it, but they look like random, there must be a difference by looking at the correlation, I think, maybe. As you can see in this case, they are pretty random above and below.
Are these particles affect the shape of this surface?
No. They are no. They do not change the fluid. No. There is no interaction between fluid and particles. They are invisible.
I think I missed the thin line, what called the thin line is
Yeah.
And which is the physical mechanism in the real ocean? Which are the physical mechanisms that make that line is at that depth? What is it, 100 meters?
I don't know. But well, the thing is that at the surface we have all type of forcing, so solar radiation. So here you may have mixing and convection, so this works only until a certain depth where solar radiation attenuates until it completely dies. Yeah. So this makes maybe convection works. Yeah. Yes.
Questions? I have one. So usually particles fall down, and this can be applied to phytoplankton in particular.
Yes, but not
You
only.
know any real measurement of this?
Of which?
Phytoplankton distribution.
No, I don't have it. No. The only things that I have is that you can really, it's really hard to find, but is the thickness of the layer. So really large scale measurements. And yes, I have it, but they don't know always gives you all the parameters. So for instance, the size of the particles or the density of the particles. So it's difficult to make a comparison in many things, but I think it's possible.